The last presenter from this session is going to be Chris Scullion. Where's Chris? Come up. So Chris works for the consulting company Trinity. They are one of the experts in modeling, and they offer a couple of suites of modeling software as well. Chris is going to talk about air dispersion modeling for odors and give us a good practice overview.
Hey guys, I'm here to talk about modeling. I'm going to try to make it interesting and fun. It could be a really dry subject, but I think if you understand the fundamentals behind the model, you actually appreciate it more and can apply it to the real world a bit better. So keep in mind, my presentation here is very centric to North America because we use the AirMod model quite a bit in North America. In talking to different colleagues out there from Europe, I know that they use their own European models. So what I'm suggesting are best practices that we can use not only in Ontario, but across Canada and the US. Fundamentals will still be the same, but perhaps other models might be used. So just keep that in mind. Also, this is a tool amongst many tools to assess odor. It's not the be-all and end-all. And just like any power tool, you can cut your hand off if you're not careful. So just keep that in mind, and let's look at some best practices. So my whole goal is the how and why we use the model. I want to get that across to you just so fundamentally we know what we're doing. Go into just the different types of models and why we chose AirMod, conventions and considerations, limitations, and finally just some conclusions and recommendations. All right, a simple diagram. If we had to choose a place to pick where we know the maximum concentration of odor in any given time, the easiest place to get that is actually at the stack. It's not subjected to a lot of the meteorological phenomenon that you would get at ambient locations. The stack, if you were to test at the stack, you'd have to make sure you also get worst case conditions, so the facility operating at a maximum scenario. If you're careful with your source test, you're going to have good source data. With that source data, we can predict the dispersion and distribution of that concentration of odor to areas of concern, which might be a fence line, could be residential areas, it could be condominium top floors. The long and short of it is that a model is always fundamental to the source data. Now, source data is not just involving the stack, it's also meteorological conditions, fundamental. So the first presentation in Australia, they don't have good, accurate, complete met data sets. Therefore, the model might not be appropriate for them. Again, it's a tool, know the limitations. The physics and geometry of buildings are quite complex. They affect plumes in a variety of different ways. We need to know this when recommending a model, and that's fundamental to what we're going to be talking about today. Because if we're looking at fence line concentrations, or if we're looking at how receptors are impacted, it's not necessarily just ground level that's important. It's not necessarily the fact that there's a tall stack that's important. It really depends. If I was to build a condominium right next to that tall stack, we could have very high odor impacts at the top floor and nothing at the bottom floors. So, another objective overall is we need something that's practical to the industry. It has to be applicable across the board, cost effective. The small dumpling houses have to be able to use this assessment in the same way that Ford or GM might be able to use some similar assessment. If we can find a way that is consistent, we have a good way of understanding what the odor impacts might be. So again, dispersion models, it's no secret, they're used across the board already for air contaminant dispersion. What we're going to do is look at how do we manipulate the model in such a way that we can actually deal with odor. All right, so we don't necessarily want to dive into the most complicated model when going into an odor assessment. Typically, there's a hierarchy in which you strategically proceed down in terms of complexity. To make a long story short, the refined Gaussian models are recommended for a good odor study involving many different sources at a facility and understanding what the impacts would be at many different receptors around the facility. So the Gaussian model of choice would be AirMod. Now, there are other models out there like CalPuff that are Lagrangian. Certainly CalPuff would be acceptable for odor, but for the practicality purposes of applying this across the board to an industry, we think AirMod's the better choice. Now, the advantage of AirMod is that it's a preferred model by the US EPA. It gets lots of support, not only by US EPA, but also by regulatory agencies in Ontario. There are many states that pre-process metadata and provide that to consultants, to industry to use. A benefit of taking advantage of AirMod is that you have access to all of this easily accessible information. AirMod's also very well scrutinized by US EPA. So as you can see, a performance evaluation of AirMod, this is specifically for complex terrain. They would do this for a variety of different model test cases. And AirMod has exceeded basically it's the best performing model when compared to the other possible Gaussian models out there. So if you look at the graph, I just want to give you some context. We have error bars right about here and here, which that's a factor 2 level of error. So basically you can see the tolerances the error mod's working within. And you can also see that for this specific case, it's slightly actually over predicting what the model concentrations would be. So it's a tall order to model something with AirMod. It's not necessarily straightforward. And even to ask a small facility, I like that dumpling house example because that's very realistic. We see that a lot in just everyday real world applications. There's a lot of inputs have to go in. So we need to be sensitive that these are, it's the real world phenomena that need to be incorporated. It's the actual site conditions that need to be accounted for, the building geometry. We need a good understanding of terrain, receptors. It's not a trivial task. It's not necessarily overly complex either, but it's looking at a variety of different inputs. So this is the goal of what we're trying to get at the end of the day, which is a nice concentration isoplyth. I like to use the word contour just to better understand it. Now, intuitively, you could look at it and you could say, well, why, Chris, you're getting higher concentrations at the boundary, at the fence line, and it's becoming less and less of a distance. And not necessarily that intuitive. If you were to have taller stacks, you might see the isoplyth be affected in a lot greater ways. For example, it might drop off further off. You might get the highest impacts further away from the facility, not exactly at the fence line. So one of the limitations of looking at the Gaussian model in general, and this is just an equation not to scare anybody, but just to show what one element is actually missing, is we have these coefficient dispersion factors which are defined by the term sigma. So in that term, we have a sigma y and a sigma z. What's missing is a sigma x. It's because Gaussian model is a steady state model. So what's happening is you get your dispersion's happening in two different planes. So if you can imagine the wind's going down the stage where my arm's pointing, dispersion's happening across the breeze and in the vertical direction. The transport's defined by the wind speed. And that's happening if you were to model any time period. The steady state is saying that you have steady state conditions occurring across the board, and that's how it's being dispersed. So the long story short is that if I was to take a line and bisect any of that diagram, any of that plume, we would have conservation of mass at each location. So if we were to get into more complex Lagrangian models like CalPuff, that actually might change with time. But that's sort of one of the overarching simplified assumptions that we have when looking at the AirMod model. So here's the most important, I think, part of the presentation, which is what are the conventions for odor? So realistically, we model odor almost the exact same way as we would for any other contaminant, which is why the model is convenient. Now, the protocols that are very specific to odor are as follows. The first and foremost is that this principle that distinct odors are modeled separately from one another. So I haven't heard that concept talked about yet. How you define whether odors are distinct or not can be a process which is debated. One way that we've done it in the past is send it to an odor panel for characterization. They compare it to an odor wheel and try to quantitatively provide us, using graphical form, a representation of whether or not an odor is distinct. So it's one element to consider for any sort of impact assessments you guys may be involved with. Now, the second is just a simple convention that odor units are dimensionless by nature. We apply a pseudo dimension of meters cubed, so it works with the model. It's a fundamental convention that's just used in the case of an odor assessment. Finally, time averaging, we've heard a lot about this, very important. AirMod does a 1 hour time average by default. And in order to manipulate the model, you're going to have to use an equation to time average it appropriately, and I'll explain that in the next slide. And the scaling factor in AirMod, for those of you who are familiar with the model, we go from grams per second to micrograms per cubic meter. So if we were going from odor units per second, we don't want to be in micro odor units per cubic meter, so we simply need to change the scaling factor down to 1. Now, Ontario is really great because it prescribes a lot of processes for how to handle 10-minute time averaging periods, and they suggest this formula. The one takeaway from this is as you move lower in terms of time average, so if your time average decreases, your concentration will increase. So what can we get and what can we expect? Here's a sample windrows plot for just a site. And just some things to take note of is what's the predominant winds, but what's predominantly also the low wind speed conditions. So I want to just talk about that. I'll highlight that later. But from a plot like this, where can we expect the maximum impacts to occur? So for this example, the maximum impact would occur in the direction. I'll just go back for a second. By the way, windrows, it's always blowing from that direction. So on the opposite side of the facility, we're going to have maximum concentrations occurring. And in this case, it's due to a low wind speed condition. So low winds can actually affect things very close to the property line. So what's the limitations of the model? Well, long story short, AirMod has always had trouble with low wind speed conditions. It's a known problem with the model that US EPA is addressing. Now, they've introduced some what's called beta options to deal with low wind speed, but as of yet, they're not regulatorily accepted. So if you were to do an assessment using these beta options, keep in mind it's not necessarily approved in terms of what the regulatory accepted protocols are for the model, but it may improve accuracy. So AirMod also obviously relies on 1 hour steady state conditions. There's a lot of potential for error that can result from that. Again, I think the solution for it is the time average. By reducing your time average, you deal with some of the uncertainty that may come from a 1 hour steady state condition. Also, keep in mind that there's just user error that can happen. We use metadata typically from regional airports or wherever it's accessibly provided, and it may not be the best representation. So I've put on the Science Center and the Toronto Airport. We also have an airport to the south, actually, where Porter's located. And you can see, since it's close to the lake, that airport may be more representative for any sort of site that may be also closer to the lake in that area. So there has to be some discretion used for what metadata you're applying. So the long story here is that the input is always vital to the model. In fact, I think it's the most important thing. Without very strong input, which involves a very rigorous stack test that's done, say, in triplicate to make sure you have good quality odor data, you will have questionable results. Now, obviously with this rigor comes good panel also evaluations. Keep in mind that the odor panels should also have a rigorous protocol of calibrations done to their assessors. Different panels may provide different results, and I think some scrutiny is required in terms of what panels you're selecting to get the odors. So overall conclusions and recommendations. Quite basically, we recommend the AirMod model for North American applications. Again, it's not the be-all and end-all. Lagrangian models certainly can be used. There's no problem with it. It's just for the use of the industry, it makes the most sense in North America to go with AirMod. Frequency analysis, very important if you have any sort of elevated exceedances. We need to know not just what the maximum level of odor is, but how often is it happening. Again, consider using the beta algorithms that are provided by US EPA to address low wind conditions. It's something to consider. And finally, obtain good source data and make sure that your time averaging periods are addressed accordingly. So if you want some modeling resources, US EPA has, you can download AirMod for free from that location, and there's plenty of guidance to use. I included the modeling guideline from Ontario because I find it's actually quite good to understand how the 10-minute time averaging works and how to incorporate the model for shorter time periods. So without further ado, if you have any questions, please let me know. Thanks.
Any questions?
Hi, Chris. What about in mountainous areas or areas close to large water bodies? Would you still recommend using AirMod?
Yeah, in some ways. In close to large water bodies, potentially. Well, it depends what you define. Like I would use AirMod, for example, to model a site around Lake Ontario for a short-term odor condition. I don't think that's necessarily incorrect. I think for larger, when you have plumes that can be transported over distance, and during that transfer can also, so within hour to hour, move in itself, a Lagrangian model might make more sense. So terrain in mountainous regions might be more sensitive to issues like that. So in that case, again, I think that there should be some thought put into whether or not you actually should be using a more advanced model and that kind of thing. However, I'm not sure if you want to necessarily in all cases go with the most sophisticated advanced computational model to deal with that. So.
And just one more question. Does AirMod, is there a beta version or anything like that that will do sub-hourly like there is with Kalpa?
That's a good question. So not that, I'm personally not aware of if there's a sub-hourly beta version of AirMod, but if there is, certainly, I'd like to see how it performs. I don't know if there's a performance evaluation for that, but it would be definitely something to look into.
Yeah, Kalpa, you need to have sub-hourly meteorology as well, but in some regions that's possible.
Yep.
That's another useful thing for other assessments as well.
Thank you so much. Any other questions?
I have two questions. Both of them are not related to order, but more. First of all, more using AirMod close to lakes or what kind of approach you are taking right now that you are successfully modeling? So what does it mean successful in this case, and what kind of iterations you are making to, for example, AirNet or NetFile that you are using for this model?
Okay, well, so successful, I think, should be defined by whether or not that your modeled approach for a specific facility is in line with the observed conditions. So if my model right away is not telling me that I'm getting odor impacts, and yet I'm experiencing complaints, or if I'm physically smelling odors, I know I need to refine the model in some way, shape, or form. Before going into the MET data side of it, and the AirMet side, I would definitely look at the physics of the building and what's going on. Typically what happens is I find there would be sources missing from the models, particularly fugitive sources, which are difficult to quantify and also to identify when doing a full site inspection. So that's the first place I would look, and I would just cross-reference it. If the model doesn't agree, you always have to be refining the model to come to some sort of agreement. And if that's not the case, it might not be the right solution for what sort of impacts you're observing.
So, regardless that you have receptors located between the source and the shore. So, doesn't mean which location of these receptors you are considering.
Sorry.
If the facility is located right on the shore, or you have some receptors which are still located between the lake and the facility.
Okay, so if you, so you're saying there's a facility near a shoreline and receptors near a shoreline?
Yes, between the water and the facility itself.
Okay, so in that case, the thing to do would be to make sure the met data is processed accordingly to account for that. That's really the long and short of it. Like, to make sure the receptors don't change in where you locate them in the model or anything, but the met data needs to address that. So you need to reprocess the met data to account for that kind of condition.
The second question was just what kind of professional opinion why Hopewell accepted Kalpa for this guideline PM 2.5 assessment here in Corona. the only one municipality which is asking for CalPAF to be used.
So there's a municipality that's asking for CalPUF for PM 2.5?
Yes, exactly. It's Oakville bylaw.
Oh, Oakville. Oh, yeah. Yeah. So, in my understanding, I've attended some meetings on the Oakville bylaw, and they're really concerned about the airshed as a whole. Like what's happening in the larger part of the airshed, what sort of influences there are. Whenever you look at that kind of level, CalPUF is more ideal for that level of assessment, because we're looking at long-term, like not just like 10-minute averaging. We're seeing how is PM 2.5 accumulating over a longer period of time. So maybe in that sense it makes sense to use CalPUF, but I'm not necessarily agreeing with the bylaw just because of that, though.
Thank you.
Thanks.
Thank you. Any other questions?
I have a question. I'm curious, assuming that all the input variables are very well estimated,
Yeah.
very accurate, can you give a best estimate about the result of the calculation?
Okay, well, I put some thought into that, and I think if you were to take just odor units in general, depending on the chemical, I think that the results will vary. I think that you'll have some contaminants that are very consistent, and will show, like that EPA diagram, will show a lot of agreement between observed phenomenon and actually occurring phenomenon, or predicted phenomenon. But I have a feeling that for other compounds, which are more susceptible to changes in the atmosphere, that degrade faster with light, that react more with oxygen, actually, you might be off, and the model might be over-predicting it. Also, I'm not sure that there could be some cases, potentially, where two different distinct odors could theoretically combine and actually make a very large, very smelly odor. So, in that sense, if you wanted to iterate your model, I think the best way of doing it is to have all sources potentially emitting at full blast with the odor, and see what kind of assessment you get from that. And if it's not agreeing with what your observations are, refine the model down and work from there. So it's kind of a structured approach. I hope that answers the question a little bit.
Well, because the practice is that the odor is quantified in a lot of ways. I was very impressed by the speaker this morning. He said we have to use it relative, but a lot of regulations use it absolute figure. So I'm curious, how big is the measurement error of the
Yeah, so right away, I'll just tell you right now. So if you're held to like a 1 odor unit standard at a property line, I think you could be out by a factor of 2 right away, just inherent to the AirMod model, just inherently. Add to that all the uncertainty that comes with the odor panel, with the measurement, with just other influences at stake, and you could be off by even a larger degree. And it could be in the positive direction or the negative direction. It's really hard to know. So yeah, should we be working in terms of absolutes? No. And I should be careful. Ontario doesn't have a 1 odor unit standard. It's not a standard that was created. It's a target that sometimes is written into an air permit as a compliance measure, but it's not necessarily the norm.
Thank you. Anything else? While he goes over there, I just wanted to ask something else. For particulate, it makes sense to have a timeout of 10 minutes. But for odors, where you sense them instantaneously, you don't sense in an hour and 10 minutes, even in 2 minutes. What's your thoughts? What should be the step then? Should it be 5 seconds? What should we do?
I think we have to live in some world of reality. And I think that if you were to smell something for 5 seconds and then it just goes away for the rest of the day, would you call the MOE and complain about it? I think that's a question to ask ourselves. And if you think the answer is yes, if the smell is that awful, it made you throw up, then perhaps that would be a valid, condition. However, I think there should be I do believe some time averaging should be considered when we talk about an industry as a whole or a province as a whole, if we're going to look at it from some sort of modeling perspective.
This question is good point. And one question, the comment is you said that we need to have some reliable data in inputs.
Yes.
And definitely that's something highly important. If you have some crap data in inputs, you have some crap results. So that's really the case with the model. We see that quite often. Regarding the data and the accuracy of the data, you say, okay, you need to have something that with a good sampling, 3 samples, triplicate samples, good analysis of the odor concentration and so on. That's a good point. I think it's even before that, what you have for modeling is what they give you as an odor concentration or an odor emission rate. What is important is the strategy and the design of sampling. It's when you take a sample, because you can be at a sample where you have some high emissions or low emissions. So it's where it's important is the design of the sampling strategy and not so much the data you will put there.
Yes.
Even if the data should be accurate with an appropriate analysis and so on.
So I think that's a really good point, and I've been involved in a number of stack testing projects just throughout my career, and fundamental to a good stack test program, like completely, is the production description of what the scenario is, and it has to be rigorously monitored and controlled because your data is only as good as what it's representing. So that's absolute, yep.
That's very point. The other question, and I think Adrian touched that a little bit, how do you deal with the intermittent emissions? That means the emission that occur, very rarely, something that is intermittent and very rare. How do you
well, yeah, currently, so what we do in Ontario is we always model a worst case maximum scenario. So if it happens once a month and that's a maximum, it would still be representative of the site. So in theory, if you can control that one maximum scenario and it reduces your odor to a point where there's no compliance issue or no complaints, you've dealt with it. But if you can't, then you're in this gray area that people have been talking about of what do you allow and what do you not allow. So yeah, intermittent odors, short answer is that yes, they're in the model at worst case.
Okay, thank you so much. So that concludes our first session. We'll come back 15 minutes after the hour.